quicksaw.org, we are SMU-RFS, an innovative team of professional engineers who design solutions to the most complex problems of today. I am Alec Siems, high-level sprint director and electrical engineer.
I'm Skylar Schapiro, and I'm a computer scientist.
I'm Lanuza-Brown, and I'm an electrical engineer.
I'm Elise Lebiga, and I'm a mechanical engineer.
I'm Carmen Leung, and I'm an environmental engineer.
I'm Francesca Brogden, and I am a computer scientist.
In many third world countries, clean water, which is vital to life, is very hard to obtain. Getting to water in general is very hard in the first place because the water sources are in very secluded areas. And sometimes getting to these secluded areas means a trek through difficult obstacles such as gravel, uneven terrain, local hazards, and even fire. Our goal is to make access to clean water more viable and abundant. We will do so by designing a robot that can autonomously navigate its way to water, take a sample, and remediate it.
The objective of the SMU-RFS development team was to design and build an autonomous robot capable of locating water in a variety of locations, test the temperature, turbidity, and pH of the water, apply an amount of remediation solution sufficient to return the pH of that water to 7, mix the solution into the water, and return to its starting location. Due to the wide range of challenges that the 4 research zones prevent and the team's intentions of solving all of them, the SMU-RFS development team determined that every aspect of the robot must be able to function in a variety of environments. The design activity imposed upon the SMU-RFS development team several constraints, the most significant of which was the short time provided in which to create a working product. Creating a fully operational prototype capable of functioning autonomously in all 4 zones would have been a difficult task, even if we could have devoted the entirety of the semester to it. In addition, the design team had essentially no experience with this level of professional development, and thus had to allocate a significant portion of the available time to learning how to operate as part of a multidisciplinary team within a semi-professional development environment rather than actually designing, constructing, or testing the robot.
We measured our coefficient of confidence based on what we knew our robot could accomplish and its relative consistency. A major factor was its significantly lighter weight. After watching a few teams compete, we realized that we were not so far behind the curve. Also, we discovered some rule changes to the competition. For example, we learned that we could use multiple programs for the competition, rather than one long program for each obstacle. This helped us because rather than having to completely restart when our robot cut out, our robot could just move on to the next task. Based on all these factors, we determined our coefficient of confidence right before the competition to equal 70.
Due to time constraints and sensor unreliability, our team decided to hard-code the majority of the robot's path. The process of getting to and entering each obstacle is the same. First, the robot will move forward 3.5 feet. Then it will take a 90-degree left turn, moving forward slightly. Then the robot will take a 90-degree right turn prior to reaching the obstacle. The robot will continue moving straight, bumping into the wall in order to realign itself, and then moves backwards 3 feet. The robot will take a final 90-degree left turn and move forward until the robot gets a reading from the tape that outlines each obstacle. When the robot makes its final turn to face the obstacle, the robot continues to move forward until the light sensor reads values of 1000, indicating it has sensed a black line. Once a black line has been sensed, the robot will run the barcode method. Within this method, the robot is able to read the barcode by the number of times the light sensor switches between 1000 and 900 values, indicating a change between white and black lines. The number of times these switches take place indicate the number of black lines. Once the robot is able to identify the obstacle, the robot moves according to the hard-coded values that allow it to navigate within the obstacle towards the water. The robot has specific ways of navigating within each obstacle. For instance, in the fire and elevated obstacles, the robot will move forward after having read the barcode until it bumps into the wall. It will then move slightly backwards, taking a 90-degree right turn and head towards the water well. After having run the remediation processes, the robot will move backwards and take a slight right turn to head towards the wall in front of it. This allows the robot to realign itself so that it can back up straight, take a 90-degree right turn, and move forward outside the obstacle. In the maze obstacle, the robot moves forward after having read the barcode and bumps into the wall in front of it. It moves slightly backwards and takes a 90-degree right turn to move forward again and bump into the wall in front of it. It then backs up slightly, takes another right turn, and heads forward towards the waterway. After running the remediation processes, the robot will back up into the wall. Then it will move forward slightly to take a 90-degree right turn. Then it will move forward again, bumping into the wall, moving backwards slightly to take a 90-degree left turn, and then it will move forward again to exit the obstacle. In the gravel obstacle, the robot will move forward, turning slightly right to reach the water. In order to exit the gravel obstacle, the robot will back up, turning slightly left. Once the robot has exited each obstacle, the process remains the same for the robot to reach the center. The robot will move forward approximately 5 feet. It will then take a 90-degree turn and then move forward in order to be in the center of the grid.
Our robot's design was based on the idea of simplicity. By constructing a lightweight and compact robot, we were able to achieve many objectives, such as navigating through the maze with minimal difficulty. Our original design consisted of a 14 by 8 inch rectangular frame with one DC motor attached to the upper right gear and the other on the bottom left gear. The treads proved to be difficult to attach given our small design. However, we managed to create a way to maintain a trapezoidal shape approximately 3.5 inches tall. The base for the treads was later widened to have greater ease when traveling from the change of height from playing field to the obstacles. In addition, after the second sprint, a second platform was constructed which added space and provided a place where the battery could rest. The crane was extremely simple in design. However, it caused many problems throughout the design process. Due to the servo's low torque, the crane could not handle the weight of all the testing sensors. 2 joint springs were later added, which better supported the crane but inhibited it from reaching too low or too high for the gravel and elevated obstacles, respectively. Finally, after some last-minute adjustments, both the crane and the servo were raised, significantly increasing the range of the crane and reducing the tendency of the servo to cut the program. As the figure depicts, the original crane only rotated 60 degrees, while the improved design could rotate 90. The following images show the top, front, and side views of the robot. The overall robot was 14 inches long, 9.5 inches wide, including the treads, and 15 inches tall, measured from the ground to the top of the crane at its natural position.
Upon examining the pH probe, we discovered 2 issues. First of all, the Arduino did not have a BNC connector that the probe could directly interface with, requiring us to solder together an adapter. Secondly, the pH probe itself output too little voltage to be read by the Arduino, which required us to construct an amplifier. Initially, we believed that we only needed a single op-amp to boost the signal. While technically achieving this goal, we were introduced to a completely new issue. Now the signal was far outside the range that the Arduino's analog pins could read. After consulting Professor Cleveland and Professor Gosney, we were presented with a modification that added a second amplifier, a diode, and variable resistor. The second stage regulated the voltage to go from a little under 0 volts to a little over 5 volts, which kept all of the pH values we needed within the Arduino's range. Our next step after design was to recreate the circuits temporarily on a breadboard for testing. In this stage, we decided to wire the turbidity and pH sensors together to one power source and switch. This saved us on both parts and batteries in the long run, and created a nice little package for the circuits, continuing with our robot's compact design. After successful testing on the breadboard, we mapped out the layout of the PCB on photocopies of the boards provided to us. Here we were able to work through some interesting layout puzzles involving the pins on the ICs and the locations of contacts on the boards provided to us. The resulting board was very clean and easy to probe for testing, only requiring us to cover the joints with electrical tape in order to prevent a short on the metal frame of the robot.
Our lightweight design had the most significant effect on our results because it enabled us to turn in tight spaces, climb inclines smoothly, and have less of a point reduction. Also, our simple crane design made it easier to adjust the height of the sensors for each different reservoir. Our crane design contrasted with almost every other group's crane design. Our robot, taking about 8 to 9 turns per challenge, had very few problems with navigating to and from the water reservoirs. This video shows the simple approach we took at getting to each challenge. The factor that hampered us the most in navigation was the fact that all movement calibrations, including turns and going straight, change when the battery is supplying a new voltage. The remediation sensors did not perform how we had hoped. The pH sensor was close to the correct value, however, the calibration was still incorrect. This table shows the voltage values that were returned by the pH probe with different pH solutions. It also shows the bit values that the Arduino converted the voltages to. The turbidity sensor was only returning values within 10 points of each other, signifying that the voltage was not amplified enough. However, the stirring motor and neutralizing solution pumped worked as expected. On this first challenge we attempted, our robot's turn calibration was completely thrown off. However, we accounted for a little bit of this in the programming as discussed in the code section of this presentation. We were very close to exiting the challenge, even with skewed calibration.
None of these results would be possible without the efforts and coordination of our team. What made our team so successful was our ability to work efficiently and utilize our specific strengths toward the progress of the robot. For example, each member was assigned a task relevant to their major. The mechanical engineer played a major role in the structural design. The computer scientist concentrated on the programming, and the electrical engineer constructed the remediation circuits. In addition, several members were interdisciplinary, assisting in other concentrations of the design. Characteristic of every team, SMU-RFS had its shortcomings. Our busy schedules rarely aligned, limiting the amount of time we could all work together and share information. In order to make up for this drawback, we found it best to work in pairs, allowing a second opinion on the task and keeping everyone effectively working. Regardless of this strategy, most of our meeting times were made late at night and consisted of efficient work. In the beginning stages, our team found it difficult to communicate openly. It was not until after the developmental retrospective that we learned to identify our strengths and further apply them for our progress. After our team discussion with Professor Yarborough, we discovered what was working, what needs work, and that we were not as far behind as we thought. One strategy we applied was keeping a to-do list of what needs to be done and creating a shared Dropbox folder to exchange important files. In the end, from this assignment, we have learned to better communicate amongst our teammates, apply our specific disciplines towards a complicated task, and meet a deadline amidst the demands of the outside world. Our task was difficult, our time was limited, but our teamwork was incomparable.